In this video, we will talk about the convection diffusion equation, and then we give an interpretation of what is this convection diffusion equation, the meaning of this convection diffusion equation. Those who are working in fluid mechanics, they know that there is a famous equation, Navier-Stokes equation. And if we write down the x momentum equation, the x momentum of Navier-Stokes equation, there are two main expressions which describes the motion of the fluid. On the left hand side, we have convection. This term over here, sometime this term is dropped when we have steady flow. Then the convection equation becomes like this. On the right hand side, you can see that there is viscosity and second order derivatives. This term is called diffusion equation. Diffusion equation. So in summary, we have convection, we have diffusion. This is an extreme example of convection diffusion. In this video, we talk about the convection diffusion equation, but first for constant velocity, linear term, here it is non-linear due to this term. And there is a pressure gradient. Okay, suppose, let me just raise it down over here. Suppose we have a circular cylinder and we assume that the circular cylinder has inflow and now we have to introduce some quantity that describes convection as well as diffusion. And previously we saw that we had one equation, partial q by partial t, partial by partial x, and here we had some flux term. The flux term means that the quantity that enters into the volume or into the region. So if we want to introduce only the quantity, for example, u bar q, then our flux becomes f of q is equal to u bar q. U bar is velocity of the fluid and q is the density of it can be a density, it can be a pressure. So this is for advection equation. But suppose that we also have diffusion. I discussed diffusion in previous video. If in case we have diffusion term, and there is a famous law which says that there is Fick's law, there is Fourier's law, and that law says that, for example, Fick's law says that we had, for example, minus beta and partial c by partial x in one dimension, in one direction. Then we have, if we say that this, for example, this quantity is minus b partial q by partial x, and this term is called the Fick's law. So what we need to do, if we want to introduce convection plus diffusion, then we have a flux. We need a flux like this. I'll write down the dependence of this flux on some quantity. For convection, we need minus u bar q, and for diffusion, for example, here it will be plus. For diffusion, we need, for example, minus beta partial q by partial x, and in short notation, we write it like this. Now you can see that here we have q, which can be anything like pressure, temperature, and this is the derivative of that quantity. This is actually the Fick's law. If Q is temperature, then it is Fourier's law. Here, this is for the convection equation, when some quantity transported from one place to another. So there are Q, we write over here Q, and then we have Qx. So it will depend on Qx. Remember that Qx is partial Q by partial x. So we put this term, this flux, into equation 1. So we get partial Q by partial t plus partial by partial x, u bar, which is a fixed velocity, q minus beta partial q by partial x is equal to 0. We can write it like this: partial q by partial t partial by partial x u bar q is equal to beta partial square q by partial x square. I applied partial derivative on this quantity. For example, I applied this over here. This becomes minus partial by partial x beta partial q by partial x, and beta is a constant. Sometimes it is a constant, but it can be a function of some other quantity. So this becomes partial q by partial t, and we can see that this u bar is just a constant. So this will come out from the derivative, and we have u bar partial q by partial x is equal to beta partial square q by partial x square. So what we have q, which is a function of x and t. And when I wrote the Navier-Stokes equation, it looked like this: partial u by partial t partial u by partial x v partial u by partial y mu partial square u by partial x square partial square u by partial y square. This is written without boundary layer assumption. You can see that this q is acting as a u in Navier-Stokes equation. This u bar may be a constant over here, but in future we will see that this will be a variable, and this if you compare, then u bar equal to u, and this q, this variable q has q is equal to u, and so on. The beta will be equal to mu. Since this is only for x and t, but here u is a function of x, y, and t for the time being. Okay, so this was all about convection diffusion equation. Thank you for watching.